So good morning. It's a great pleasure to welcome the third lecturer of the school, Professor Badri Krishnan from Radboud University in Nijmegen and at the Albert Einstein Institute. Badri is a relativist with a wide range of interest, starting from mathematical relativity, going all the way up to gravitational wave astronomy, including gravitational data analysis. And he has made very important contributions in all of these topics that he has worked. So basically, he invented this this idea of dynamical horizon that he will talk about today. And later, he switched to the search for continuous gravitational waves at the Albert Einstein Institute. And later, to the search for compact binary coalescences and using them to do various kind of sciences, including testing relativity. And so it's great that he's coming back to his topic, probably closest to his heart. And personally, also, Badri has been a close colleague and mentor for me over the last 15 years or that, ever since I was a graduate student. So it's personally also it's a great pleasure for me to welcome Badri back to Bangalore.
Thank you, Ajith, for very kind words, and it made me feel old that I'm your mentor. And since, but okay, good. Thank you, and it's very nice to be back here. So the plan for the lecture is to introduce the topic of quasi-local black hole horizons and various aspects of it. So we'll cover the mathematical aspects, the numerical aspects, and the applications to gravitational wave astronomy. So let me start off with where essentially the previous speaker left off. Thomas left off in his study, in his presentation of the Penrose strata diagrams. So I will start off by telling you why, for our purposes, they're not very useful to talk about event. I mean, the diagrams are, of course, extremely useful, but event horizons are sometimes not, or usually are not. So let me, in fact, first spend the first part of my lecture today just doing that. So this is where Thomas left off. So you have the Penrose diagram for Schwarzschild, and as Thomas said, you can ignore all the other axes. This is sort of the thing that you will focus on. So this is the black hole horizon. This is the R equal to 2m surface in Schwarzschild. This is null infinity, and that's a singularity. So the rest of the, so just to again repeat what you learned in the previous lecture. So if I have an observer here, the observer can fall into the black hole. Once he or she crosses this black hole, then after that, classically speaking, you can't come back out because any causal inference from here can only go into the singularity and you can never cross back the event horizon again, right? So that is all good. So I want to now, first of all, present to you a different way to characterize the surface of a black hole. So one more property that is very important, and that is sort of complementary to the presentation you heard today morning. So to do that, in fact, so I need one extra ingredient, which is the mean curvature and the notion of the expansion of a null vector field. So I will introduce that slowly, but before that, let me sort of give you another overview of why this event horizon notion is not very useful in dynamical situations. So to do that, let me generalize the Schwarzschild picture and introduce a dynamical ingredient into that, and that will use the Vaidya solution. And I will illustrate the difference between the Schwarzschild and the Vaidya case, and then we can discuss the different aspects of the event horizon in the two situations. Okay, so in the Schwarzschild case, you realize that this is the event horizon, and this has this causal property, and this is the surface which R is equal to 2m. So everything sort of agrees here. So let me now write down a different metric, just a small change from what you learned in Schwarzschild, and this will be, you got to think of Schwarzschild in the Eddington-Finkelstein coordinates. So that is so this is the metric that you learned today morning. So this is the Schwarzschild metric in ingoing Eddington-Finkelstein coordinates. So this V is the ingoing coordinate, and R is the radial direction. And of course, there's the angular part of the metric, which is not really relevant for this discussion here. So we'll make just one small change to this metric. So we can say that this m is not a constant, but a function of v. Okay. Now you might imagine, well, introducing this constant is a solution to the Einstein field equations. Well, of course, any metric, I can just calculate the Ricci tensor, and that I would say, well, that is what the matter ingredient is for that metric, right? So for at any metric down, I can calculate its Ricci tensor, its Ricci scalar, write the Einstein tensor, and that should be then the matter content in the system, right? The only question is, does that matter field satisfy some reasonable conditions, like the energy conditions? And in this case, I will not do the calculation here, but it turns out to be the case that indeed, if you do calculate the stress energy tensor for this metric, the result is essentially what is known as null dust. Okay? So it is just different particles not interacting with each other, all of them is infalling into the black hole, and in fact collapsing to a black hole. And in fact, we can draw the Penrose diagram quite easily for this case. It's not that easy, but okay, I'll just give you the result. And intuitively, I think it should be more or less clear. Just make sure I get all the factors right. Okay, so this is then the simplest case. This is the metric you would have for a collapsing star, the Penrose diagram, and this is then the event horizon. And in fact, if in this case you look at the r equal to 2m surface, what you find is a surface like this. So let me describe what is going on here. So this is the coordinate v that is going along here. It's a little bit tricky sometimes to get all the different. But okay. So this is the coordinate v. The null dust, so before v, there is nothing happening in the space-time. It's just Minkowski space. Starting from some initial v, let's call it v naught, the infall starts. So null dust is falling inwards, and it collapses, and then this is then the metric. So this m of v is meant to be 0 up to this v naught. It then starts off at 0, then increases, and reaches a maximum value at some point. And then this is then the event horizon you get in that situation. And let's say the null dust collapse stops at this point, call it V1. So by the time you reach V1, m of v will have reached some value m at V1. Let's say it's a constant value after that. So this part is then just Schwarzschild. And this part is just flat space. And this portion in between is the part when the black hole is growing. So the black hole then starts off, with 0 mass and increases to the final mass that you have, the Schwarzschild black hole. This portion is entirely identical, at least in that locally speaking, to a portion of Schwarzschild spacetime. And this portion is just Minkowski space. And this is the event horizon. You just go to the end, go to time like infinity, trace back the last null ray here, and that is then the event horizon. Now, this is the surface where r is equal to 2m. In this case, this is not the event horizon. I haven't told you so far anything special about that surface, but if you just put r equal to 2m, you get a particular surface in your spacetime, and it will be this, some surface here like this. But important, it is not the event horizon, in fact. Okay? Of course, in this portion it is, but here it is not. And you notice also something which might bother you a lot, which is that if you look at the event horizon, it goes back here. In fact, this portion of the event horizon is in flat space. So you could have observers living here who might happily live in this portion of space-time. They can cross the event, they can't come back out, but they can go into the event horizon. But it's flat space. So there is no experiment that they can do to detect the presence of this event horizon. There's nothing they can do. So they can create a lab, they can, let's say they have infinite resources. They can do all the experiments they want in this portion of space-time. They will never realize, or they can never realize that there is a black hole there. The black hole we mean here, then event horizon. Is that point clear? So this is telling you that this is a toy example. This demonstrates to you that event horizons are not really useful physical objects in this sense. So you can ask questions. So so I want that to sink in, right? So don't think of event horizons as useful things at this point. We think of these as being surface of black holes, and okay, in a sense they are. But they have this feature that there's nothing useful that you can do with them at this point. And even worse, I mean, if you think about this line is R equal to 0. So at this point, the event horizon has 0 area. It grows. So in fact, the black hole is growing here. It's even worse, right? Not only is there an event horizon in flat space, it's even growing. So if you thought that, well, a black hole grows because there's stuff falling into the black hole, well, there's nothing falling into anything here, right? It's just flat space. There's no radiation at all. There is no matter, there's nothing. And still the event horizon exists, and it's even growing in this portion of space-time. So if you had some notion that, well, the event horizon, there is some flux of radiation through the event horizon, I integrate that, and that gives me the change of the area of the event horizon. Well, in general, such a law is not possible at all for event horizons. And this is an example of that. Because no matter what definition we might have for fluxes of whatever you want, in flat space, they should vanish, right? There's no radiation in flat space. Yes, starting from here. Well, that is the calculation, right? So if you just trace the null edges, I think the Penrose diagram sort of shows you without having to do a calculation. You can calculate this, the shape of the surface, and it is precisely this shape here. Yes, so the point is that the event horizon extends back into the flat space before any matter starts falling in. Well, depends what you mean by horizon now. So the event horizon is just simply the surface, right? And on this surface, R is increasing. It starts at R equal to 0, and it ends up at R equal to 2m, with m being the final value of the mass. But at this point, this is R equal to, at this point, the horizon is 0. It grows. It reaches eventually what you expect in the Schwarzschild portion. But in doing so, it has to exist in flat space. Which means that it is in fact not existing, but it's growing in flat space. Okay? And the reason this is happening is simply the condition of the event horizon, right? Event horizon is sort of surface from which no observer is sort of the boundary of this black hole portion, right? So once you enter, you cannot come out. But what is in and out? to know that, you have to sort of wait till the end here. Or if you wish, you start off, the way you calculate the event horizon, you start not at the beginning like an initial value problem. So normally you say, well, in classical mechanics, if I tell you the position velocity of a particle at a given time, I can predict its position at any later time, right? But for the event horizon, it's the other way around. You say, well, what will it be at the end? And I integrate back in time to get to the beginning, right? In other words, this surface here knows what will happen at the very end. It knows that there will be infalling matter falling. It knows what the final mass of the black hole will be. That is the final value of this function m of v, that's here. So already at this point, the event horizon knows what will happen in the future. Yeah, so the angular part is all here, so that is not relevant here. Yes, so I said m of v, right? So m of v is meant to be 0, and then it starts. So if you wish, if I want to plot m of v, just think of some function like this. This is v, this is m. So let's say this is v naught, this is v1. So it's exactly 0 here. Let's say it grows, and then it reaches at v1. And let's say this is the final mass. Right, so this is m of v. So this is, let's call it m final, right? It's completely smooth. It's not analytic, of course, but okay, it's smooth. I can choose a tan hyperbolic function if you wish. I start off at 0, it grows, and it reaches a fixed value. Yeah. So this portion of m of v, so up to this corresponds to this part here. The growing part is up to v1, and then it's a constant after that. Any other questions? So this is the sort of an important point here, right? So which is that event horizons, at least as they are defined, as they are presented, are not always useful in all situations. And even more, you cannot have, as a matter of principle, some local equation which says, well, some matter fell into the black hole, and that made the black hole grow, or some radiation energy crossed the horizon, and that made the horizon grow. Right? Because again, in this case, it's flat space. There cannot be any fluxes of any kind like that in flat space. The black hole is still growing. So therefore, there cannot be, as a matter of principle, any such equation in full nonlinear GR. And these problems come about because the black hole, the event horizon knows what's going to happen in the future. Well, but this diagram, well, it's all a global thing, right? So you have to know what the full space-time is. So I have to prescribe for you some function m of v. I've picked a function like this. So, and that leads to then this diagram here. Yes, so that is this Minkowski portion of space-time here. Yes, so they are far away initially. It takes them some time to fall in. And I mean, you will notice that the r equal to 2m surface, in fact, knows when the black hole, when the matter is starting to fall in, right? So this r equal to 2m surface only exists after v naught. Because before, when m is 0, r equal to m is just r equal to 0, right? So okay, so this is an important point. I can spend more time on this. If you don't appreciate this first part, the rest of the 5 days will not make any sense to you. So this is important, okay? So let's make it even worse. So let's now think of the following situation. Let's draw this here. So let me now, in fact, make it even more evil, right? So let's say that the infalling matter initially starts off as 0, it grows, it becomes a constant, and then grows again. Now, who's to prevent us from choosing such a function, right? Let's call it V2, and let's call this V3. Okay. So this is then some mass M1, this is some mass M2. I can choose that, right? I just say, well, there's some infalling accretion of null dust. Initially, no 0, it switches on, becomes a constant, and switches on again. Right? So it switches on, switches off, switches on again. So that's in this portion, and in this portion, there is no infalling null dust. Yeah. It's spherically symmetric, so it's all spherically symmetric collapse accretion in this case. Well, it's a shell, yes. But it's an infinite extension shell. It can continue as long as it wants. So here, this is a finite shell, right? So this is going on for a finite V. So it is a finite shell, but it can, in principle, extend infinitely. But here, it is a shell, yes. So how should this situation look like? Well, that's not that difficult to figure out. So it's a little bit tricky to do this, but let me try it in the following way. So this is the part that I described so far, right? So I have then infalling null dust here. But then it switches on a bit later. So in fact, and let's do it like this. Then it grows again. So what I thought was singularities was actually not. It's like this, right? And this, in fact, is the actual event horizon. Okay. So this is the R equal to 2m surface. So it increases initially, becomes a constant. It increases again and reaches some other value at the end. So what I thought of was the singularity, what was null infinity. That is not this one, but actually it's moved here. Right? So in fact, an observer here, as I argued, could not tell you that there is a black hole formed in that space. You might say, well, okay, fine, this is some theoretical problem. What about this part here? So this portion of spacetime is exactly Schwarzschild, right? It's a Schwarzschild of mass m1. So in fact, you could have a civilization living here who could explore the black hole, they could figure out its properties, and they would think that this is then the black hole horizon. Right? And they might even call it the event horizon if you wish. But they don't know that, in fact, there's going to be more collapse a little bit later. So in fact, for the full global spacetime, this is even not the event horizon. This is the event horizon, in fact. And some observers on the civilization would be in this portion, which would be inside the event horizon. So this surface, which is the R equal to 2m surface, and this is exactly Schwarzschild, this portion of spacetime, right? And this is what you think of as the event horizon of a Schwarzschild spacetime. But this example shows you that it doesn't have to be. It is some useful surface. I mean, you do feel that this surface should be useful in some way or the other. But whatever it is not the event horizon. Yes. Yes, good. Yeah, exactly. So I prescribe this for you. So you have to prescribe this for you indeed. Well, so the goal here is to sort of give you a toy problem, right? Which is not, it's not realistic collapse, obviously, right? So there's no spherically symmetric collapse in nature of this kind of null dust. So this is just an sort of a toy problem. It says, okay, if we had this kind of a collapse, then these are the properties of the different horizons that you get. And to illustrate that, the event horizon itself is not a useful construct in these cases. So there's something missing in our, so far about what a black hole is. Well, no, it's not, right? So we just see it here, right? So this is R equal to 2m in this portion here. So the R equal to 2m surface is this. That's right. Right, so this is again, so this portion is also then Schwarzschild, but with a different mass. So this is Schwarzschild of mass m1, this is Schwarzschild of mass m2. Right? So let me just, again, I think people might be confused. So V0, V1, V2. Well, I mean, when the matrix falling, then the R equal to m surface is growing. We will discuss that in a lot of detail in the next in the rest of the lecture and the next days. So the properties of this R equal to m surface will occupy us now for the next lectures. Okay? Because it is not the event horizon, right? So the event horizon is, in fact, I go to the end, and I trace back the light trace, and I get this surface. It is simply not the event horizon. I don't know what more to say. It is, all of the definition calculated is not the event horizon. Yes. Yeah. But again, I want to clarify, there's nothing hard about the event horizon. The definition is completely clear. There is no ambiguity in the definition of event horizon. Right? It just says you wait till the end, go to time like a future time like infinity, trace back the last light rays, and that is the event horizon, right? So there is no, again, there's not a difficult thing for the event horizon. In any dynamical situation or otherwise, the event horizon can be defined, perfectly mathematically clear, and it is this surface. There is no ambiguity in the event horizon, but you're right that all the problems happen in dynamical cases. And I want to make the point that, well, even this R equal to 2m surface, like the one here, may not be the event horizon because, again, all the problem comes about because the event horizon knows about the endpoint of your spacetime. Tell me what's wrong with causality here. Yeah, so it's a null surface, right? So it's nothing, again, when you say breaking causality, it means it's something physical is happening that is causing causality to go wrong, right? It is just a null surface. I mean, there's nothing magical about the way, it's just a null surface defined in a particular way. And this particular way happens to have the condition at the future infinity. Hmm. That's right. I mean, this is a. Tell me what's wrong with the example, right? I mean, there's, if you've not seen it before, you might be surprised. Well, but this is, I'm just following the definition of an event horizon. That's all I'm doing here. It's just that no matter how advanced civilization living here, they're not gods, right? They cannot know what's going to happen 20 million years later. Indeed, you're right. That's how it is. And it makes no difference to their life. They proceed with their lives as always, and nothing changes. Well, everybody will eventually go into the singularity. That is sometime 50 million years and a billion years. Who cares? For your day-to-day life, it will not make any difference. Even that is true even here, right? I mean, do the people living here care that, well, they are inside the event horizon? Well, they're in flat space. I mean, as far as they're concerned, their lives go on as always. And nothing goes wrong for them. Yes. Yeah. Yeah. A little later, yes. Mm-hmm. Mm-hmm. No, all that happens when they fall into the singularity. Well, I mean, somebody living here might also eventually fall into the singularity. That's fine. That's sort of fate. I mean, poor chap, right? I mean, but who cares? I mean, if, as I said, people can live here for millions of years and they will notice nothing wrong. So yes, that is sort of the important point here, right? Because again, I want to go back to the definition of the event horizon. What is the event horizon? And it is that, well, I go to this point, which is future time like infinity, or the end of null infinity here, trace back the light ray, the last light rays there, and I will get then the null surface here, a light-like surface, like this. Exactly. Exactly. But it's not wrong in a very specific way, right? So it's not even that, you can think of the event horizon growing as some flux of matter falling into the black hole. Any other doubts or questions? This should be sort of surprising to you, right? Because I guess you've never been told that event horizons are useless. So this is somehow. Yes, it's satisfied throughout, yes. Well, it depends what you mean one way, right? So it's, as we will learn, this is in fact a space-like surface. So space-like surface means once you cross it, you can't go back. So it's a one-way surface in that sense, of course. And this is a null surface. So once again, once you cross it in this direction, then you can't come back out. So this thing of being a one-way surface is something completely trivial. So it's not a fundamental, it's just an important thing, but it's nothing special about the event horizon in that sense, right? I think any space-like surface, once I cross it, I've gone future in the time. I can't go back, I can't cross it again. So any space-like surface is a one-way surface in that sense. So this thing about an event horizon being something that you can only cross one way, okay, that sounds fancy, but it's nothing fancy at all. So any other questions or surprises? No, I mean, again, emphasize again, this is simple. I mean, I think you're referring now to these surfaces, right? R equal to 2m. But that is not the event horizon. So this is not the, if I just follow the definition of the event horizon, it is not the event horizon. I mean, you call it the event horizon, but it is not the event horizon. The event horizon is only this null surface and that's it, nothing else. The event horizon is defined everywhere. I mean, it's defined for all V, but you start at this point and to integrate this light rays backward, null backwards in time. Exactly. Yeah, that is the point. So you need to even, and the definition is completely clear, but to construct it, you need to know what happens at I plus. You have a question? So again, there would be, again, yeah, that's a good question. So maybe I will touch upon that in the later, maybe in the last lecture. In that case, event horizon will shrink. Okay, so it will be, in fact, not a null surface in that case, but then, okay, the final fate of that is still a question for research. Maybe it just shrinks and goes to 0 and there's nothing left after that. Could be, right? You mean, how do we know what happens after we cross the event horizon? Yeah. Well, I mean, again, I repeat, I'm prescribing for you here a specific mass function, right? Mass function is growing, so that specifies the entire matter content I want in this model. So that determines everything. That determines the whole space-time, this whole structure. Right? There's nothing that I have to fudge here. So this is simply, you have to accept this, and then the rest follows. So again, that is a good question. So again, I had meant this to be only the classical aspect of the picture, but if you bring in quantum mechanics, yes. So I think it should be from this R equal to 2m surface. So that should be the relevant thing for Hawking radiation. What do you mean by static? So, and so this, for example, this portion here, this is R equal to 2m. It's a fixed area. Again, it is this is not the event horizon, right? Yeah, it could be. We'll talk about that today, but it doesn't have to be, right? So I mean, in general space-time, there's no reason such a surface should exist, right? It might in some cases, but it's not relevant here, right? So why do you bother about that in this case? So more questions. This is nice. So any other questions? Okay, so let's go on. Let's proceed. So with this, yeah, sure. It could be. So we can discuss that. I mean, there's arguments on that question. So and that takes us beyond the topic at the moment. But yes, it's a debatable point. Yes, I agree. Yes. That is the key question. That you touched upon the right question. So then the thing that I wanted to take away is that what you mean by a black hole in a dynamical situation is really, not so obvious. So you might think it should be the event horizon. Yes, it is completely well defined. And it is in fact, this is in fact the event horizon, but it's not useful. It's not useful here. It's not useful here. It's not useful here. So maybe that is, that is maybe the one takeaway message from this part of the lecture, right? What is a black hole is an interesting question that is not fully understood in a fully dynamical situation. All the things that you know about Schwarzschild, everything, it all, it is useful. I'm not saying, you shouldn't know that, but understand the limitations of that. Okay, then let's go on. Well, this already was 45. Okay, fine. Okay, so the next part, I need to introduce some mathematical notions that we will use later on. So I will do this slowly so that all the different aspects of it are understood. Okay, so the first thing I want to explain to you is the geometry of submanifolds of a given manifold. Okay, so so imagine now some manifold living in a bigger space. Let's say the full space has a dimension, let's call it big N. And let's say the submanifold has a dimension, let's call it M. Okay. So N minus M is known as a codimension of the surface. This, for the moment, leave it to be anything. Could be 1, could be 2, 3, 4, whatever, in high dimensional space. Okay. Now, the next thing I wanted to sort of explain to you is covariant derivative. I'm sure you've studied, all of you have taken a GR course. All of you know what a covariant derivative is. And all of you know what the Christoffel symbols are, right? So, and you know that given a metric, how to get the Christoffel symbols. So that is, I think all of you know that, right? I wanted to tell you that, in fact, the notion of covariant derivative is something more general. Okay, it will be very important for our purposes to understand that. So imagine that the full space, now for the moment, just for the next 5 minutes, just think of a manifold with some metric. Let's call the metric to be GAB. Okay. Now, given the metric GAB, I can calculate its first derivatives and combine them in the usual way, and I get the Christoffel symbols for that, right? So that is one notion of a covariant derivative. But it's important to understand that covariant derivatives are a more general notion. Okay? So when I write this symbol and I say grad of x, so this means a covariant derivative in the direction of a vector field x. Okay, so this is the same as XA and then the question is, well, what properties should this thing satisfy? So its goal is to differentiate tensors. We should differentiate functions, differentiate vector fields, and so on. What should its properties be? Well, the first one is that acting on any function, this is simply the normal derivative along a function. Okay. So in fact, it's a bit tricky thing. If I use this index x with this grad x all the time, I will often use this grad A symbol here. It simplifies things. So this is the same as saying that and partial A just means the partial derivative for the coordinate A. That's a normal partial derivative. Then the second condition is that grad A of some f times x satisfies Leibniz rule. So it's let's call it xb. And in fact, this applies to any product. So I can take a product of any two tensors, and the result of that will satisfy Leibniz rule of differentiation. Okay. Then I also want the following. So it should be a symmetric, so it's called a connection, this derivative operator. So it should be a symmetric connection in this particular sense. Okay. Then the important point for the existence of a connection, why do you define this, is to differentiate a vector field and to define the notion of parallel transport. So I can take any curve. I mean, I presume all of you have seen that, so I will not go into detail on that. If you have any curve, if I say that along that curve, the covariant derivative of some tensor vanishes, so that tells me that starting from any point on the curve, I can parallel transport that tensor field and get at any other point of the curve. Okay. And here, I mean, there is no, of course, there is one special the connection that is coming from the metric, from the Christoffel symbols, but this is a more general notion. And in fact, this will play an important role, right? When we have, especially when we have null surfaces, this will be an important thing, that the metric itself does not determine the connection fully. But at this stage, just for the moment, just understand that this notion of a connection is different than the notion of a metric. It's sort of a different beast altogether. And exactly, yes. Yes. And again, just to remind you of that, so the special connection, the singular by the metric, is the one for which the metric is covariantly constant. But this is not always true, right? So this is a special condition. Okay. Good. So now let's go back to this case. Again, just to tell you why we are studying this, right? So all of you had the question here. All of you sort of thought about the R equal 2m surface in one form or the other, right? All of you must have felt that should be useful, that should serve some purpose at the end of the day, right? And these are now submanifolds of this bigger spacetime, right? You could think of at any given time, this R equal 2m thing is a sphere. The sphere is growing, or staying constant. Or you could think of the full surface here like this as a three-dimensional manifold at the end. Right? So therefore, let us sort of study the properties of, first of all, submanifold. Let's understand that properly, and we'll then come back to this picture here, and we'll then understand fully what this means. Okay, so now let's proceed. So now let's understand properties of this submanifold. Now, the first notion you have to understand is how to project things tangent and orthogonal to the surface. Okay, so think of any vector field X for the moment. Again, you must have learned from linear algebra or from the notion that I can project this into a component that is tangential to a surface and one part that is normal to the surface. And this is true for any codimension, right? So it doesn't matter what the codimension is. Okay. So this is then X perpendicular, and that is X tangential. So I'll often use sort of notation in which I don't have an indices, so index-free notation, sometimes with indices. I hope that all of you are used to that. So in this case, I will write this relation in the following way, which is that X is some portion that is tangential to the surface and some portion that is orthogonal to the surface. There's one important thing that you have to always keep in mind. This definition works only if the surface is not degenerate, if it is not null. Okay. Why? Because you need the metric to define orthogonality, right? So I want to say that, well, I have some, so what does X perpendicular mean? It means this vector has to be orthogonal to any vector tangent to the surface. We take any vector to the tangent to the surface, take this vector X perpendicular, take the inner product, which needs the metric, right? And that has to be 0. That is how you define x perpendicular, right? And again, just to give you sort of a preview of what we will see tomorrow, which is if this were to be a null surface, the null vector is both tangent and orthogonal to that surface. So this hidden in here is the assumption that, you know, this x perpendicular and x tangent and x perpendicular do not have are disjoint sets. There cannot be any vector that is both tangent and perpendicular to the surface, which will happen a lot now for us starting from tomorrow. But for the moment, assume that that doesn't happen and that this submanifold is a non-degenerate submanifold. So the induced metric on that submanifold is non-degenerate, in which case I can always do this decomposition like this. Clear? Good. So now let us say that the full manifold has some connection, let's call it, right? Then the question is, what is the connection induced on this submanifold? Okay. So, by the way, shall we want a short break, 5 minutes? Or coffee or so? No? We'll go on? No? Okay, no break, good. Okay, good. So let's do this. So let us say that I want to now, first of all, for the metric, you see that if I'm given a metric, GAB, that defines you a metric on the submanifold, let's call that HAB. Right? How do I do that? Well, I just say, if I take any two vectors tangent to the surface, x and y, I define their inner product, x dot y, according to GAB, XA, YB. But here, x and y are tangent to the surface. So I'm just restricting the action of the metric for the inner product only to vectors tangent to the surface. So this is saying that I'm pulling the metric back onto this submanifold. Okay. In fact, as you will realize, if I take any one form, let's call it omega A, I can restrict its action to the submanifold by saying that, well, the action of omega on any vector field XA tangent to the surface is just given by, if omega were to be a one form in the full manifold, right? I just restrict its action to vector fields tangent to the surface. The result is a one form that is living on the surface. Yeah, x and y are, yeah, x. So here now, x and y are always tangent to the surface. No, I'm defining it like this, right? So I'm saying, so the point here was that GAB can act on any, I can take the inner product of any two vectors, no matter tangent or not, using G. But when x and y are restricted to lie on that submanifold, then that, in fact, this is like a definition for H. So I say that, in other words, HAB, XAYB, is defined to be this way. Okay. Similarly, for any one form, omega A, but just by restricting its action to vector fields tangent to the surface, I get a one form living on that surface. So that's a very, very important thing, which is that for vector fields, I need the metric to sort of do this decomposition of tangent and orthogonal. For one forms, I don't need the metric. For one forms, I just restrict the action of one form to vectors tangent to the surface, then I get a one form living on the surface. Again, these are all notions that are completely obvious in the usual cases you look at, but we will not be restricted to those cases. For that, I will not go through this whole drama about all of these different details of these definitions, right? To summarize that, if I have any index that is up, from that gets projected onto the surface, and orthogonal to it requires a metric. If I have an index that is down, I can always restrict the action onto the surface and get a one from living on that submanifold. Okay. So again, keep in mind, not only is this notion of a connection more general than just what you're used to, but it's important to distinguish between vector fields and one forms. You can use the metric to raise and lower indices, but don't assume a metric now. So go back to the original definition of what a one form is. Okay. And this tells you automatically that, well, a one form can be pulled back to the surface with no extra structure. But to pull back, or to call it pull back, or to restrict, project this onto the tangential surface requires the metric. Is that clear? Again, if you don't understand this, tomorrow will be very, very confusing for you, okay? So you better ask questions if this is not fully clear. So if you want to do this in this sense, if I have some, let's call it the injection operator. So I have a manifold here, let's call it S. And this is the full manifold is M. So the manifold S by itself is an object in its own right. So when I do this injection, I'm sort of putting this S into this M. I can take one forms here and pull it back to one forms here. I can take vector fields here and push it forward to vector fields here. That part is quite easy. I mean, given any tangent to that surface, it is automatically a tangent, is some vector field in the full manifold, right? So this direction for vector field is sort of obvious. The push forward of a vector field is obvious. And pull back of one form is sort of with this extra work is also obvious. But when you do this operation of projecting orthogonal and tangent to the surface, that requires a metric. That is not covered by this sort of a structure. That's right, yes. But and I don't want to bore you with this more abstract nonsense here, but let's not do that. So just think on the usual way that you're used to, but just go back to what a one from and what vector fields are. Then, so now let us do the next step of starting from the connection in the full manifold, how to get a connection on the submanifold. Okay. And the way to do that is I say, well, I want to sort of start off with grad x of y, which tells me that starting from any vector field x, I can differentiate a vector field y in the direction of x. That is what this thing means, right? So this is, in usual index notation, this is the following thing. Okay. But this is a vector. This is a vector field now. Okay. And this I can then decompose into some component tangent and orthogonal to the surface, right? So this is then grad x of y, tangent plus y, that is orthogonal, right? Now the part that is tangent, that in fact is the covariant derivative on the surface. Let's call it dx of y. Okay, so if grad is the connection, or nabla is the connection on the full manifold, then D, I say, is a connection on this submanifold S, defined in this way. Right? So I just say that dx of y is exactly the tangential component of that. That's a definition, okay? This is now the connection on that submanifold. And I'll leave it for you to check that this satisfies all the conditions that you expect for a covariant derivative. Okay. So just to summarize, given any manifold M with a connection, which is this nabla, by this projection, I can get a connection on any submanifold. Yes. Yeah, it is that you have to do a little bit of work for that, but yes, it is the same. It's just one extra line. So I won't do all the steps. Think about it. Maybe in tutorial we can discuss it, but yeah, you get the same. Now this guy here, the orthogonal part, is interesting for us. And by the way, I mean, I should say that this definition of D only again works for a non-degenerate submanifold. If it is null, then this definition does not work. Because we decided that this decomposition is only sensible if, or is only unique in the case of a non-degenerate submanifold. Okay, any questions? All right. So this part is what you might turns out to be the extrinsic curvature of all the other things at the end. So there's some little notation, which is that given a metric here, GAB, the induced metric here, let's call it HAB, that is called the first fundamental form. So this is the full metric. This is the first fundamental form. Okay. This guy here is then, well, the second fundamental form. Okay. So this has a special notation to it. I will just call it with this index 2, x, y equals okay. So let's understand what this definition means. I start off with two vector fields tangent to the surface. So x and y have to be tangent to the surface. Given those two tangent vector fields tangent to the surface, this thing produces for me a vector field orthogonal to the surface. Okay, so if you like it mathematically, then I take two tangent vector fields to that submanifold, call it S, right? Call it some point X, or let's call the point P. So this is the vector field, the space of vector fields, vectors are orthogonal to the surface at any given point. So this second fundamental form takes two vectors tangent to the surface and gives me a vector orthogonal. And its definition is this. I do grad x of y and project it orthogonal to the surface. So if you're used to just index notation, this might take some getting used to, but it is simpler to explain the geometry in this particular way. Okay. So again, since this might be unfamiliar to some of you, so I pause. So if you have any questions, any confusions on this definition. Sorry, TPSY, what do you mean? So, sorry, this is perpendicular. So this is the space of vectors orthogonal to the surface. So TP of S is a tangent tangent space at any given point P to the surface S, and TPS perpendicular is the thing that is orthogonal. Yes, so I just take then this, X is from here, Y is from here. I take both of these and the result is. So this quantity, the second fundamental form has the structure. It takes two vector fields, two vectors tangent to S, and gives me a vector orthogonal to S. Again, for those of you more mathematically inclined, what this thing does is to decompose the tangent space at any point P of the manifold M into a TP of S and the direct sum of TP perpendicular to S, right? So that decomposition is saying that, well, given any vector on the submanifold, on the full manifold, I can decompose it uniquely into a direct sum of these. So, and these two spaces have no common elements. So the intersection has to be 0. Okay? But that's just a fancy way to say what we just discussed. Right. So the thing is, if the, so here, okay, let me do this more slowly. Then so this is saying, okay, let me do this slowly. Okay, so this is the tangent space at the point P of the full manifold. I decompose that into a part that is tangent to the surface and a part that is orthogonal to the surface. So TPS is the tangent space at any given point PS to the surface. TPS perpendicular is the space of vector fields orthogonal to the surface at the point P. Okay, there's a direct sum, but there's one more condition is that these two vector spaces should only have the zero element as a common element, nothing else. There should be no vector that lies in both. For a null surface, that is not the case. The null direction lies in both of these spaces. It is both tangent and orthogonal to the surface, right? So that is what I mean by excluding non-degenerate case here. So in this discussion, I'm excluding the case when this surface can be null. We'll discuss that tomorrow, but for now, we restrict ourselves to this. Any other questions? Yes, so that is what a pullback means. Pullback means I just restrict its action to things tangent to the surface, right? Yeah, so I get from G to H by this pulling back. So the first fundamental form, this H, is sort of easy to get just by pulling back. The second fundamental form is this notion. So again, just some more geometric insight, which is that this first, sort of you want to describe the geometry of how a surface is embedded in larger manifold, right? So the induced metric, which is this HAB, there's a pulling back, that is one part of it. But the extrinsic curvature, second fundamental form, tells you how it is deformed in this larger space. All right. So let's study some properties of this second fundamental form. So that will be critical for us. The first thing you can check is that it's a symmetric thing, which means that grad, this 2 acting on X and Y is the same as this 2 acting on Y and X. How do I show that? Let's apply the definition. So 2 of X and Y is just and this other guy, 2 of Y and X is grad Y of X. So the difference between the two, so that would be 2 acting on X and Y minus 2 acting on Y and X is grad X Y minus grad Y X, and the whole thing. And this thing is just the commutator of the two vector fields. And this does not require the covariant derivative. This is a combination of the derivatives such that it only requires partial derivatives. And there's a theorem in this field known as Frobenius theorem, which says that if X and Y are tangent to the surface, then so is their commutator. Okay, to make it, this sounds an abstract thing, but it really is not. Okay, so let us imagine here, just give an example. If I have some coordinates on this surface, let's call it X, call it Xi, then the partial derivatives along this are the partial of del Xi, right? All of the other coordinates are constant. That is what defines the surface. So let's say that I have coordinates Y and X, and the Y's being constant define the surface S. So that is the X's here, okay? If I take partial derivatives with respect to only x and y, the y's are always kept fixed. So all the partial derivatives here commute in the usual way, with the y being a fixed thing. So that is all that Frobenius theorem really means. Okay, so this is then 0. That is saying that if x and y are tangent to the surface, so is their commutator. So this is 0, so that means that this is a symmetric. Okay, is that clear? Any questions about that? So this might be unfamiliar to people doing sort of a standard GR course in the physics sense. Have you ever seen this kind of thing before? I just want to understand the background a little bit. So not many, right? So okay, some of you might have, but this might be an alien sort of way to present what you might think of as a simple subject. But believe me, this will be useful for us later. Okay, so that is this property of the second fundamental form. That's important. Then let us now restrict ourselves to, well, let us give some examples now. Okay, this will be, then we'll come back to this physical case of interest to us. So I can go to this point here for the, so one more. All right, so the next thing would be, just a minute. Okay, this is taking much longer than I actually planned. Fine, I suppose. Okay, good. Okay, so now let's look at some examples. Okay, so let us think of a codimension 1 surface first. So this might be the thing that you're most used to, which is a space like hypersurface in a Lorentzian manifold. Okay. Okay. So this is then the usual case, space like surface sigma. In a Lorentzian manifold. Okay. So therefore, in this case, there is one time-like normal to the surface. Let's call it little m. Okay, so what does second fundamental form mean in this case? So in this case, the space that is orthogonal to this surface sigma is just one dimension. It is just this, anything along n will be the thing that is orthogonal to the surface, right? It's a one-dimensional space. So therefore, in this case, this 2 of x and y will be some tensor field, let's call it K, AB. Oh, the other thing, so there's one more thing I should mention before this, which is that this quantity 2 is a linear operator acting on both x and y. Okay. How do I see that? Well, it is linear in x, obviously, right? Because if I multiply x by any function, this just comes out. By the symmetry, the same thing holds for y, but you can see it directly. If I multiply y by some function, when y comes out, the orthogonal projection kills it. So therefore, this 2 is a linear operator on both x and y. So that means that there must be some tensor of this kind. Minus sign is for conventional reasons. Okay. So therefore, there must be some tensor, call it K. And the x and y are just acts linearly on x and y. So that is what this thing means. And in this case, it's a codimension space 1. So the result has to be along N. Right? And this K is known as the extrinsic curvature of this submanifold. So this gives us a definition that you might be used to, that we'll get that now. So this guy is just, by definition, it's this orthogonal component, right? Well, to save space, let me just write it like this. I'm not putting an index here, so just to be clear that this is something along N. So this has an index C, and this one has not, but I hope that you can understand what I mean here. So let us now contract both sides with this N. Okay. So that is the same as doing the following thing. I take grad X of Y, contracted with N, then the N goes away. And the minus sign goes away because n dot n is, n is unit time like normal. N dot n is -1. Okay, and this guy is just a way to write. Right, so this thing only means this. And now just looking at y is tangent to the surface, n is not. So I can just take the n inside the derivative. So this is then negative of xa, yb, grad a, and b. Right? And then now comparing both of these guys, I see that the extrinsic curvature is the covariant derivative of the normal, but pull back to the two surfaces, to pull back to the submanifold. So this is only true for x and y tangent to the surface, right? So that means that I'm calculating this grad A and B and pulling it back to the surface. So that is the extrinsic curvature that you might have known from other. Right? So in the codimension 1 case, that is the one that is the most familiar to you, I guess. In that case, the second fundamental form is the extrinsic curvature. So I guess more of you know the extrinsic curvature, right? So this, I hope that all of you have learned that at some point. Is that true? Can you show your hands if you know about extrinsic curvature in this sense? Okay, that's much better. So the second fundamental form is nothing mysterious. So in this special case, this is the same as what you're used to. But things are more interesting when we go to codimension 2 surfaces. Okay? And that will then take us to trapped surfaces. And so let us now discuss that. That's right, yes. So it's the, or if you like, it's just the pullback of grad A and B with a negative sign. The usual way you project these two indices with the H, but it's not required for the covariant indices. Yeah. That's right.
So you can take the splitting of GAV also locally as completely block of matrix, right?
Yes. Well, it doesn't have the matrix structure depends upon the coordinates that you use. If you choose coordinates correctly, then it will have this block structure, like you said.
So the coordinate exactly like that. There is no cross term. Then it would be exactly like the block diagram, right? It is a direct.
Yes, that is true. For the vector field, it's a direct sum. Metric, you have to be more careful. That inverting the metric is then a tricky thing. So then that we should be careful. At the moment, all I'm saying is that you get the 3 metric on sigma by just pulling back from the full 4 metric. I'm not saying anything about the block structure of this matrix as a matrix. Okay, so just in case you're wondering, so I think we're almost out of time, in fact, and I'm not even halfway as to what I planned for today's lecture. And all the exercises are for things I was going to now cover. So what we will do then for tutorial, I'll just be there. You just ask questions, any doubts on this thing, and we can do the detailed calculations starting from tomorrow. Okay. Okay, good. Thanks, Ajith. This is a lot of work to make these 5 lectures. And obviously, I badly calculate the time I required for this. But again, more questions is better. So it's better if you ask questions than if I just rush through all these. Okay, let us now go to codimension 2. So this would be the case of some, let's say, 2 spheres embedded in the full 4-dimensional manifold. Okay, and this is sort of a very important case for us as we discuss. So by the way, for just like we have an extrinsic curvature here for the 1 codimension case, you realize that for any number of codimensions, I will have 1 extrinsic curvature for each extra dimension, right? So I will have a KAB corresponding to each direction that is orthogonal to the surface. So as a general statement, for the general embedding, you not have just 1 extrinsic curvature, but you have sort of n extrinsic curvatures, with n being the codimension. Okay. So therefore, in this codimension 2 case, you will have 2 extrinsic curvatures. Okay. And what they are will sort of be obvious in a minute. So let us now look at the case when I have, let's say, a 2-dimensional Riemannian manifold embedded in a Lorentzian manifold. Okay? In other words, the 2 metric will be, think of a normal 2 sphere, that is sort of the canonical case of interest to us, embedded in the Lorentzian manifold. Okay? So in this case, the space that is orthogonal, what is it? Anybody want to guess? Yes? It is 2, but what is the signature? Exactly. So it's a 2-dimensional Minkowski space that is orthogonal to S, right? So if I take, in this case, let's call this to be surface S. So it's 2-dimensional. The result is then all the part orthogonal is 2-dimensional, but it's 2-dimensional Minkowski space, right? So therefore, I can choose 2 null normals. Let's call them L and N, which you will not like. But the important point, I've not said what these L and N are. It's just that in a 2-dimensional Minkowski space, let's just think of here R and T, right? So that is sort of the canonical case of interest. So then I will have one L or T plus R, and the other L that is N, that is T minus R. I mean, I could have chosen here one time-like and a space-like vector. That is also completely fine. But it will be useful to think of the null vectors in this construction for our purposes. SS space, always for today, the SS space-like. Only thing was there it was 3-dimensional. Now here it is 2-dimensional. Okay. So that is why if S were not space-like, if S were, let's say, at a time-like component to it, then the space orthogonal would be purely space-like, would be Euclidean space. The reason I have the 2 null vectors, that the 2 null directions are sort of fixed. We'll talk about the normalization issues in a minute. But the important point is that the space orthogonal to S is 2-dimensional, is the Minkowski space. So I have one null normal and another null normal. Well, it's a vector space, remember. So again, we're looking at the tangent space, right? So Minkowski vector space just means that it's a vector space with the metric, and the metric has the Minkowski form, right? But in this case, I'm referring to the vector space being Minkowski, not the manifold. So there is no manifold orthogonal to S, right? So it's only vector space we're talking about. Okay, good. So therefore, now in this case, I have two extrinsic curvatures, one along L and one along N. So therefore, the second fundamental form will be something along L plus something else along N. And these somethings are linear operators acting on X and Y. Okay. So, and by the way, one more notational thing. So the trace of the second fundamental form, if I trace on the two covariant indices, that is called the mean curvature of the surface S, okay? So the mean curvature, the symbol for that is H, is a trace of the second fundamental form. Okay? So this is the mean curvature. Yes. Yes. Everything is, I mean, this is a very, very general theorem. So everything here is based on a fully, this can be the most, presented as the most general way possible, right? Which applies now not just to these two cases, but any. So this mean curvature will be important for us, and that will lead us to the notion of an expansion of these two null normals. Okay. So let us now think of what these somethings are that appear here. Okay. So let me for the moment call them as alpha AB, XA, YB along L, plus let's call it beta AB along N. Okay. Then there's an important point here, which is that the L and the N, we assume that they satisfy the condition, which is that L dot M is -1. Okay, so unlike if I were to choose them, one to be time-like and one to be space-like, then the two basis vectors would have 0 in a product. Since they are null, you can check that if I just take t plus r and t minus r by square root of 2, the inner product would be just -1 for L dot M. So this means, in fact, I can scale my L by any function. So I can choose any function, I scale my L, multiply the L by that function f. But then requiring this condition means that the N should scale as f inverse of N. Okay, so I'll choose my L and N such that they're cross normalized in this particular way. And this restricts the rescaling freedom that we have. I can change L to f times L. I can change N to f inverse times N. And in fact, I won't discuss this point here, but this is sort of the interpretation of being a boost transformation from the Lorentz group. So that is what this thing is, but we'll not discuss that too much in these lectures. But then the point is that any geometric quantity that we have should be invariant under these rescalings. And as we shall see, the mean curvature is independent under this rescaling. Sorry? F is just a scalar function. F is some scalar. So I can change L by any scalar multiplied by L. If we require L to be future directed, then F has to be positive. That is the only condition. But beyond that, it's all general. No, I mean, it's a constant at any, the function is only over S, right? So at any point, of course, there's only one number. So let us now contract this pi first with L and then with M. Okay? And by the way, it should be obvious that L is null. So L dot L and N dot N are 0. Okay. Okay, it's not, the time is up. Let me just finish this and then can you 5 extra minutes? So I'll finish then this definition, then we'll proceed there. So then, okay. So this 2 of x comma y dotted, let's say with n, should be alpha AB, XA, YB. So L dot n is -1, so that's a minus sign. And N dot n is 0, so that doesn't contribute. And this is grad x of y perpendicular dot n. So this is nothing but XA grad A by B dot B. And I do the same trick again. So this is the same as negative XA YB grad A. Okay. So therefore, you can just do the next step not with n but with L. Then you will see that in fact the second fundamental form. So it's a tensor, right? So x comma y. So this will be the negative sign. So negative and b LC. Well, let's make the x and the y to be common overall. Minus grad A LB and C. Whole thing multiplied by x. Okay, we're almost done. So then this is the combination of interest to us. So this is the extrinsic curvature along N that multiplies L, extrinsic curvature along L multiplying N. So therefore, if I do this rescaling business here, you can check that this thing is embedded under that rescaling. Then the mean curvature is a trace of this guy with the indices A and B. So then that is then the last step. So the mean curvature, let's call it H, let's call it HC, will be negative. Let's now call the induced metric on this S to be Q tilde for historical reasons with the Q tilde, which is what we will use in fact today. So then I have to use the metric in that sense. So that is Q tilde AB LC here. Okay. So this is a trace of the extrinsic curvature along L, trace along N, and these are the expansion. This is the expansion of L, that is the expansion of N. Okay. So in other words, if you imagine now from that surface 2 light rays coming out in both the direction, the expansion tells you how these light rays sort of expand as they proceed outwards. Okay. So this is the negative theta of L, expansion of L, times NC minus theta of N along LC. So this is known as the mean curvature of that surface S. Okay, and with that we will stop, but I'm happy to take any questions about this. So we'll continue. So in the tutorial, maybe I'll discuss that further, but if you have any questions and so on, you can ask in the tutorial. Any questions? Good, so then let's stop now and we'll proceed in the tutorial.